Now we want to generalize our previous discussion about the curvature of plane curves to define curvature of space curves. As before, as a vector, we can define the curvature vector to just be the acceleration vector of the curve. So now there are two subtle points that we need to address, which is a bit different from the space curve case. First of all, we need to be a bit careful about what we mean by a unit normal, because there's a whole plane that is normal to every velocity vector. And the second subtle point is that a space curve has extra dimension to curve into. Let us explain what we mean. Think of a curve on a plane as a string, right? Then we can lift this curve up at different points for it to become a space curve. We can lift it up in a different way into space so that this curve, this space curve, is no longer planar, i.e. there's no plane that contains it. In a sense, we would feel that such a curve, right, a non-planar curve, is more curvy in a sense than the planar curve, right? The planar curve is in a sense flatter than this space curve. So we want to have an additional curvature to measure how far a space curve is from being planar. We often call this second curvature torsion. So the torsion of a space curve measures the extent to which the space curve fails to be contained in a plane. Alright, so let us now address both of these subtle points. We're gonna define the unit normal and the torsion of a space curve. To that end, we want to first define the osculating plane of a curve at a point P. Right, so even though the curve gamma is not planar, at any point P there is a plane that is closest to gamma. That's going to be called the osculating plane of gamma at P. This will be the plane that goes through P and is parallel to the velocity vector and the acceleration vector of gamma. We can then define the principal normal line of gamma through P to be the line normal to gamma. Remember, we have a whole plane normal to gamma, so we want to be the line normal to gamma that lies inside the osculating plane. So it is the line of intersection between the normal plane and the osculating plane. Then we can choose the unit normal to be parallel to this line. Well, there are two choices, so we can choose either one as long as our choice everywhere are compatible. What do we mean by compatible? Well, we want to choose a unit normal vector everywhere in such a way that this is a continuous vector field along gamma. In particular, in our picture here, let's just let this be the unit normal. Okay, so now let's address the second point. How do we measure how flat the curve is at P? i.e. how far gamma is from being planar at P. Now remember, the osculating plane to gamma at P is the plane that is closest to gamma at P. So that means that if gamma is actually flat at P, if it's planar at P, then on a neighborhood of P, gamma must actually lie inside this osculating plane. Putting it a bit differently, for point Q very near P, the osculating plane of Q should be the same as the osculating plane of P. Thus we see that maybe the flatness here could be measured by how much the osculating plane turns. How much does the osculating plane change? So how would we quantify that? Well, we often think of a plane in terms of a point and its normal vector, right? A normal vector and a point uniquely determine a plane. And actually, once we have fixed a normal vector and a velocity vector, then there is a canonical choice for this normal vector, namely the cross product of the velocity vector with this unit normal. We call this the unit binormal vector of gamma at the point P. And as we mentioned, the flatness at P should somehow be captured by the change in this unit binormal. We could define just the magnitude of this vector to be our torsion, but we want to have sign torsion. So instead, we look at the coefficient of this in terms of this unit normal vector, right? And we define this to be the torsion of the curve gamma at the point P. Now the question is, how do we know that this vector is in the span of this unit normal? Okay, so let's see why. Let's differentiate this and use product rule. Now this unit normal and this acceleration vector, they are parallel, so the cross product is just going to be 0. Thus this derivative is going to be perpendicular to this velocity vector gamma naught and the derivative of this unit normal. So let's see what we know about this. Now this unit normal vector has length 1, so as before we can differentiate this inner product, right, and then use the product rule. From that we will get that this derivative must be orthogonal to the unit normal n. So this derivative vector n naught, it has to lie in this span of this b and gamma dot. This n hat must somehow lie in this plane because it's orthogonal to this n. Now b dot is orthogonal to this gamma dot, right? And b dot is also orthogonal to this n dot. So b dot must be orthogonal to this whole plane, the b gamma dot plane, this whole plane. And so if it's orthogonal to that whole plane, it must be in the span of this n. Thus we can write this b dot as a multiple of this unit normal. And this coefficient, we call it the sine torsion of gamma at the point P. So that concludes our discussion on curvature of curves. Next we're going to move to curvature of surfaces.